Alright, so when we're reading this problem, what volume in milliliters does a sample of nitrogen with a mass of 0.245 grams occupy at 21 degrees Celsius and 750 torr? When we're approaching it, we want to ask the question, what do I know? And what's happening. So especially in gas laws, you want to determine whether there's one set of conditions or two sets of conditions. You won't always have a label at the top that says ideal gas law problem. So what do we know? We know the mass and the identity of the gas, which means that we can solve for moles. We're given temperature, we have to convert that to Kelvin. And we're given pressure in torr. We need to convert that to atmospheres in order to use the value for R that we have. What don't we know is the volume. So always write these out so that you know where you're going and why. It sometimes will help you not get so tripped up with, here's an equation, what does it mean? All that. So the first things we want to do, we're told that the gas is nitrogen. So N2, that means we have 2 times 14 is 28 grams per mole for the molar mass. So if we take mass divided by molar mass, we'll get moles. We can do that. We got to convert the temperature as well. We can do that. Keep the 0.15 even though it's not significant. So when we're adding, we're limited by the place value of the degrees Celsius measurement. Just be aware of that. So this goes to the ones place, so we get to keep to the ones place. But keep the 0.15 in your calculation so you don't get round off error. Technically, I would like to use 4 or 5 digits in the molar mass as well. Convert pressure to atmospheres, and then we'll be good to plug in to the ideal gas law. Write it out, PV equals nRT. Rearrange it. Oh, convert mass to moles. I already talked about how to do that. You guys should know how to do that, but here's the setup in case you need to pause and remember. If we rearrange the ideal gas law to just solve for volume, we can do that. We got moles times R times T over P. So we're going to take all of our values from this slide, pause and jot them down if you need to, and plug them into this equation. So we've got moles, we've got R, and we've got T. Again, keep the 0.15 when you do the math, and then round at the end. And here's our pressure. Everything cancels except for liters. This is good news. And then the question asked for volume in milliliters, so then we convert 0.214 to 214 milliliters. So that's one example. Second example is within the context of a chemical reaction now. So we're ramping it up just a teeny bit. How many liters of nitrogen at 1 atmosphere and 25 degrees Celsius are produced by the decomposition of 150 grams of sodium nitride? So I have written out how to do this so that you can see it in real time as opposed to slides. Here are all the solutions. So, alright, so I've written out the chemical equation and what we know, which is that we're given 150 grams of sodium nitride and we're trying to find the volume of nitrogen produced. Other things that we know just because of our knowledge of chemistry, we've got the ideal gas law. That's how we're going to solve for volume. And we can determine the molar masses of all the species involved. We're given pressure and temperature in the question, so we need to find moles, and we're going to use stoichiometry from our reactant starting material to find moles of nitrogen. So the molar mass of sodium nitride, we've got 1 sodium atom, 3 nitrogen atoms. That gives us 65 grams per mole. So I'm going to convert 150 grams of sodium nitride to moles of sodium nitride, so then I can use stoichiometry to get moles of nitrogen and use the ideal gas law to get volume. So there's multiple steps, but it's just like a puzzle, or if you've ever tried to untangle jewelry, just follow the next line of thought through. So here's my stoichiometric ratio. It comes from the coefficients in the reaction, and that will give me moles of nitrogen. 3.46 moles of nitrogen. So now I can plug that in for N to my ideal gas law. In the problem we're given 1 atmosphere for pressure, 25 degrees Celsius for temperature. Let me convert that to Kelvin real quick. And R is a constant, 0.082057 liters atmospheres per mole Kelvin. Alright, so let's plug those in to the equation. We've got all of our things. Boom. 1 atmosphere times volume equals 3.46 moles. Let me cancel units. And my final volume answer will be in liters. Divide both sides by 1 atmosphere, and the solution we get is 84.6 liters of nitrogen that are produced from this reaction. So here's the slide with the solution. If it's any clearer for you, you can always pause and look it over. Now we're going to have you guys try one. So pause the video and give this one a go. If you got C, then you got the correct answer. If you didn't, check your work here. This is the correct setup. We need to convert the mass of carbon dioxide to moles using the molar mass. Here is an abbreviated version of R. And then temperature, once it's converted to Kelvin, is 308. Liters is given, so pressure is 0.379 atmospheres. Got a couple of other example problems. I'm going to go through them a little bit quickly because we'll be doing some practice during our class time. But here's kind of a fun one. 13 moles of dinitrogen pentoxide decompose into nitrogen dioxide and oxygen gas at 415 Kelvin in a 4.75 liter container. If it can't expand or contract, that means that volume is fixed, but pressure will change. And then if it's a container, that also means that moles is going to be entirely changing from the reaction occurring. So, what is the pressure after all the dinitrogen pentoxide decomposes? This is kind of a strange problem, but let's just draw a picture real quick. Here is my container. At first, I have N2O5. As it decomposes, it'll create more moles of gas. Let me just use the coefficients as they appear in the chemical reaction. And what will happen is that this will decompose from 2 mole equivalents of gas to 5 mole equivalents of gas. So the pressure is going to increase. We can solve for the initial pressure, but that's not particularly helpful except to maybe compare, oh, did we kind of do it right? Because we would expect the pressure to be higher. But let's just go through how you would actually find this new pressure after the reaction. So it seems like some conditions are changing, but what's happening is a reaction is occurring. And then we just want to know about the final condition, which means that we're still using the ideal gas law and not the combined gas law. So here is our balanced chemical equation. They're all in the gaseous phase. What we want to do is calculate the moles of gas that are produced. And so we start with 13 moles of our reactant, and we produce 5 moles of gas in the product side. So we've got 4 plus the 1 of oxygen. And so that gives us a mole fraction, or a stoichiometric factor, of 5 to 2. So what we have after the reaction is 32.5 moles of gas in that container. We're trying to solve for the pressure at the end. So now we have moles because we solved for them. R is a constant, and temperature was given in the problem. So was volume. So try putting this into your calculator. Make sure that you're entering everything right. Sometimes dividing can get tricky. But I get 233 atmospheres, which is an insane amount of pressure. For reference, that's about, almost 7,000 pounds per square inch, if my math is right. Oh, just kidding. About half that. Still, 3,500 pounds per square inch in this container. Alright, just a summary of solving for gas law problems. If you're not sure which one to use, just double check what's happening in the question. So if you have one set of conditions, or you're trying to find some amount, either a volume or a pressure or moles, you're going to be using the ideal gas law. If you're given 2 sets of conditions, like it says, oh, it starts at this pressure and ends at this pressure, what's the new volume? Something changing in there, you're going to use the combined gas law. Typically, if there's like a reaction going on, you'll be using the ideal gas law to relate the moles to the stoichiometry of it, but read carefully. That's not always a hard and fast rule, it's just a guideline. Alright, we have one more concept in this section 9.2. So I'll make a little video about that. Should be pretty short, and it won't be one of the required ones for Thursday, but it will help you out maybe on the homework or just general understanding. And it has a shortcut in it, so standard temperature and pressure.